Topics in post-harvest technology. Precooling methods. Hydrocooling, Part 2. Aqueous disinfectants. With hydrocooling, cold water is used to remove the heat of commodities, and this is an efficient process. However, a downside is that the commodities are being wet, and microbes thrive in wet environments. Microbes present on only a few items may be washed into the cooling water to spread to otherwise clean commodity. To reduce the microbial load in the cooling water and to inhibit the spread of microbes to clean produce, disinfectants are used. So what are the common aqueous disinfectants used with hydrocoolers? There's chlorine, chlorine dioxide, ozone, and peroxyacetic acid, which is also known as peracetic acid. Let's first talk about chlorine. Chlorine is used extensively due to its ease of use and effectiveness. Chlorine is applied as a gas, that is Cl2, as calcium hypochlorite, or as sodium hypochlorite, which is also known as bleach. Chlorine gas is the least expensive of the chlorine forms, but it is a hazardous gas as it is potentially lethal both to produce and humans. Therefore, extra safety precautions and training are required when using chlorine gas. Calcium hypochlorite is a solid that readily dissolves in warm water, and that warm water solution is then added to the hydrocooling water. Calcium hypochlorite is the same powder added to many home swimming pools. Sodium hypochlorite, or common bleach, is added as a liquid. Both calcium and sodium hypochlorite must be food grade if used in hydrocooler water. So what are some factors affecting chlorine effectiveness? First is the pH of the cooling water, followed by the concentration of available chlorine in that water. The contact time of the water with the produce is also very important. The temperature of the water will affect chlorine's effectiveness. Organic matter in the water will affect chlorine levels. And chlorine's effectiveness is determined by the type or types of microorganisms that one is trying to control. Some are easier to control than others. pH affects the availability of the biocidally active form of chlorine, which is hypochlorous acid, or HOCl. Also, if the pH is too low, chlorine gas can escape from the water, and that could potentially harm your workers or the produce that you're treating. If the pH is too high, the active form of chlorine is not available. The best pH range for chlorine is 6.5 to 7.5. Available chlorine must be present in sufficient concentration to kill the microbes of concern. The USDA recommends levels of 100 to 150 ppm of chlorine in cooling water, though often in practice the actual level is much less. Active chlorine must be in contact with microbes for sufficient time to get killed. The contact time of a product with the disinfectant water is known as the dwell time. There is usually tension between the need for sufficient dwell time and the need to get product quickly through the system to be packed and marketed. Chlorine is more active at warmer water temperatures, so the concentration used in cooling systems must be higher to compensate. At a pH greater than 7.5, chlorine combines with organic matter to produce trihalomethanes. So what are some examples of trihalomethanes? Chloroform, which may be a carcinogen, bromodichloromethane, dibromochloromethane, and bromoform. Trihalomethanes may have adverse health effects at high concentration, but the levels in produce are considered of minimal risk. The use of chlorine as a disinfectant has many benefits and is cost-effective. Chlorine dioxide, or ClO2. Chlorine dioxide is effective over a pH range of 6 to 10, which is a much wider range than for active chlorine, and it has 2.5 times more oxidizing potential than active chlorine. It's used at concentrations of 3 to 5 parts per million, and though it does not produce trihalomethanes, it can produce compounds such as chlorite, chlorate, etc. Of concern is that it is explosive at concentrations greater than 10% in air at standard temperature and pressure. Therefore, it cannot be transported in the United States and must be produced on site. It is expensive to produce, and it's toxic to humans. It also readily off-gases from wash water. Therefore, wash systems utilizing chlorine dioxide must be closed systems if workers are present. The Federal Occupational Safety and Health Administration, that is OSHA, has set an average exposure limit of 0.1 parts per million of chlorine dioxide in air during 8 hours of exposure to this chemical. Ozone, or O3. Ozone is one of the strongest oxidizing agents available, but it has a half-life of only about 15 minutes at standard temperature and pressure, so it must be generated on site. It's difficult to maintain levels above 1 part per million in water, and it works best at a pH of 6 to 8. As a strong oxidizer, it is toxic to humans at levels above 4 parts per million. Ozone is highly corrosive and requires the use of stainless steel and synthetic materials. Natural rubber seals and tubes are readily destroyed by ozone. Water to be ozonated must be filtered, as organic material easily combines with and destroys ozone. Ozone is most often produced through corona discharge, but high-energy ultraviolet may also be used to produce it. With corona discharge, air is filtered to concentrate the oxygen, which is then exposed to a high-voltage electric field. When the electricity discharges, ozone is formed. Think of natural lightning passing through air and forming ozone during a thunderstorm. Here's an illustration of a corona discharge system. The filtered, highly concentrated oxygen is fed into the tube, which has a high voltage potential. This causes electricity to discharge from one side of the tube to the other. Essentially, you form a lightning field, and as that concentrated oxygen passes through this lightning field, you get ozone being produced. With the UV system, air is again filtered to concentrate the oxygen, which is then passed through high-energy ultraviolet light, which reacts with the oxygen to produce ozone. Ozone is highly reactive, and though it does not produce trihalomethanes, it can produce a number of products such as ketones, aldehydes, and carboxylic acids. Regardless, it is generally considered safe to use, though research on potential reaction products is ongoing. Peroxyacetic or peracetic acid. Peroxyacetic acid is formed from acetic acid and hydrogen peroxide. It is a strong oxidizing agent and hence a good antimicrobial. It is a stronger oxidizing agent than either chlorine or chlorine dioxide, but has less oxidizing potential than ozone. Peroxyacetic acid is a colorless liquid with a strong vinegary smell that is irritating to the eyes and respiratory tracts of humans. It's often shipped as a concentrate, and when it's in a concentrated solution, it's able to blister skin. Currently, there are no federal exposure limits for peroxyacetic acid over an 8-hour period. The EPA, however, has stated that acute exposure of 0.17 parts per million peroxyacetic acid in air during an 8-hour period can lead to noticeable discomfort and irritation to humans. At concentrations greater than 42 to 56%, peroxyacetic acid is an explosion hazard. Above 105 degrees Fahrenheit, it may form an explosive mixture with air. In spite of these limitations, it is highly effective against a wide range of microbes, and it does not produce trihalomethanes. However, it is relatively expensive when compared to using chlorine or chlorine dioxide to disinfect. Summary points. Water used to pre-cool produce must contain a disinfectant to limit the transfer of microbes between products and to reduce decay. 4 disinfectants are commonly used in hydrocooler systems: chlorine, chlorine dioxide, ozone, and peroxyacetic acid. Chlorine is a highly effective and widely used biocide, but at high concentrations can damage or kill produce and workers. Chlorine effectiveness is determined by water pH, water temperature, the amount of chlorine in its active form, the amount of organic matter in the water, and the type of microbe being targeted, as well as dwell time. Chlorine may interact with organic matter to produce trihalomethanes, some of which are potentially carcinogenic. Chlorine dioxide is a stronger oxidizer than chlorine and does not produce trihalomethanes. However, chlorine dioxide is potentially explosive, so must be generated on site. Ozone is a very strong oxidizer and is usually generated on site either through corona discharge or via high energy UV. Ozone action does not produce trihalomethanes. Peroxyacetic acid is a very effective antimicrobial, but at high concentrations can be explosive. Peroxyacetic acid is relatively expensive compared to chlorine or chlorine dioxide, but is a better oxidizer than either. Regardless of the disinfectant used in hydrocooler water, care must be taken to ensure worker safety.